Hi everybody, my name is Ide Ezgi Onal. I'm a material science and engineering PhD student at Georgia Tech working with the Clever Group, and today I will be presenting you our work on thermoplastic dielectric coatings for the EDS devices. To start off with a very brief background beyond our motivation, as we all know, the lunar dust or regolith is a challenge for lunar exploration, and one of the technologies that has been developed to address this challenge is the electrodynamic dust shielding systems. A subcategory of these systems is the flexible EDS devices for any type of curved surface or dynamic applications. However, as my colleague Luca has already pointed out, there has been some performance degradations over time for the flexible systems due to problems such as dielectric breakdowns or arcing that are utilizing CMRGO as their conductive material. Now, what CMRGO is that it's a nanoparticle of reduced graphene oxide that we have modified by introducing some dodecyl functional groups so that it can better stick to the thermoplastic substrates that I've been using to fabricate these flexible devices. And to address the dielectric breakdown issue, we decided to encapsulate our devices using a dielectric cap layer. And since we've already been using a thermoplastic substrate, we decided that a simple thermoplastic attachment method would be effective to address this issue in an adhesive-free manner. Now, on this image, you're going to see our design that is consisting of two interdigitated electrodes of CMRGO. And on the cross-section, you're going to be able to see the particle infiltration of CMRGO from both a thicker substrate layer and a thinner coating layer. Now, how we're achieving this is that we're basically thermally laminating the bottom three material layers you're seeing at the bottom. And because our thermoplastic materials are being softened with elevated temperatures and high pressure, they are interdiffusing into each other and their chains are entangling and cross-linking. On their way, they're also infiltrating whatever CMRGO particle we have in the middle so that we can get this nice flexible composite device. I also want to highlight the selected materials that we have here. We have high-density polyethylene HDPE, polyvinylidene fluoride PVDF, and finally polysolvent PSU. Now, to test the performance of our devices, we have a multimodal testing plant involving a simple peel test to test and quantify the adhesion strength of our attachment. We have a standard compression test that is slightly modified so that we can cyclically bend our devices, but at the same time, we're also focusing on their sheet resistance measurements to track any changes to their conductivity. We have an abrasion test to see whether our coatings do indeed offer any sort of protection against the external stressors, which is the dust itself. And finally, an EDS performance test in high vacuum. Now I'll be moving on with our results, and here you're going to see the average peel force that is required to peel off our cap layer. And we're focusing on our different material groups at the bottom tier. We also have the manufacturing dwell time given in minutes, and this refers to the time that we are allowing our thermal lamination to happen. We also have respective CMRGO percent coverages that you can also see on the top left legend with the different percent coverages starting from no particles with 0% and up to a full CMRGO coverage overlap area. Now, what we have observed here was as expected, with longer dwell times and less particles at the interface, we got better adhesion. But what stands out is the green region on the right with PVDF material category. We've actually got no peels, showing an strong adhesion and fully bonding case. Now, moving on with the cyclic bending test results here, we are focusing on the relative changes to the sheet resistance indicated by delta R over R0, which is our strain over time. And I will be briefly going over each material group, starting with HDPE. Here you're going to see our coated sample indicated with the red sinusoidal waveform. It's actually showing a larger strain when compared to its uncoated counterpart given in blue. And this shows high strain resistivity, but if you look at PSU sample, we actually get a dampened signal. So we can see that the strain is partially being able to shield it by our cap. And if we move on to the last material group, you're gonna see almost a flat line with the red coating. And this is once again showing the PVDF case standing out with showing excellent strain isolation. Now, before moving on with the actual EDS performance, we finally have done an abrasion test setup. Here, you're going to see our equipment on the top right corner that uses some wheels to actually push some dust simulant onto the surface forcefully so that the samples are being abrased with the dust. And we have again taken a look at the sheet resistance measurements with two probe multimeter measurement before and after the abrasion. And by using these values, we have again calculated the relative increases to the resistance with the abrasion damage. So if one can deduce from this chart is that the coated samples initially exhibiting higher baseline resistances, and this is understandable because there is more infiltration to the polymeric dust, the dielectric matrix, with an additional cap layer on. However, if we're looking at the farthest right column highlighted in bold, we can see that the coated device is showing significantly lower changes, and they're actually protecting our internal circuitry against the abrasive dust. And we can see that with only 2.5%, PVDF is again standing out from all the other material groups that we've tested. And that's why we decided to focus on a PVDF sample for the EDS performance test here. On the right, you can see a looping video of our performance. And this is a PVDF sample coating layer with a coating layer of thickness of 20 micrometers that was manufactured using the 30 minutes of dwell time condition to get the best seal possible. And this video belongs to an applied voltage of 6,000 volts. But we started this test at a much lower voltage, and we repeated many runs until achieving this video. And even though we run many samples, we haven't seen any dielectric breakdowns or the sparks that you've seen in the previous presentation. So we are actually getting rid of the dielectric breakdown by encapsulating with a dielectric layer. So now I will be wrapping up my presentation by giving you some key takeaways and summarizing what we found with the significance. So we have seen is with the thermoplastic adhesion, depending on various factors such as the material compatibility between the layers, manufacturing dwell times, and the nanoparticle coverages at the interface. And with the cyclic bending test, we've seen there were no drastic changes happening to the relative changes to the sheet resistance. So neither with coated or uncoated devices that we have, which is confirming their flexibility for dynamic applications. And we've also seen that although the resistances might increase with bending, they're recovering upon relaxation. So it's reversible electromechanical behavior. And we've also seen our coatings providing some abrasion resistance as well. So the device is being protected against the external stress factors, which was the dust mainly in this case. And finally, with the EDS efficiency under vacuum, we've seen that the performance has been remaining effective even after the coating was applied. So this indicates that the encapsulation does not mainly compromise the dust repulsion capability. And it's also got rid of the dielectric or arcing problem that my colleague Luca has pointed out before. So we improved our design with this encapsulation layer. Finally, I also want to acknowledge Clever, Survey, and NASA for supporting my work. And I also want to give my special thanks to the labs that I'm a part of at Georgia Tech, the Schaffner and iDream Lab. I've also included my contact information in case if you want to reach me regarding any questions that you might have about this presentation. And thank you for your attention.